We build skyscraper-sized machines, fill them with explosive chemicals, and then intentionally destroy 90% of the vehicle just to get a tiny payload into orbit. This staggering waste is a requirement of our environment. To leave the planet, we have to pick the lock on an invisible mathematical cage, using specific engineering tricks to bypass the laws of physics. The foundation of this problem is Newton's third law of motion. Every action has an equal and opposite reaction. Think of a deflating balloon. As the air rushes out in one direction, the balloon moves in the other. A rocket is essentially a giant version of that balloon, designed to throw mass backward with as much violence as possible. Every launch is a brutal, non-negotiable transaction. We are buying momentum by trading away massive amounts of fuel. In 1903, Konstantin Tsiolkovsky published the mathematical proof that defines the limits of this transaction. His work describes a cruel paradox. To go faster, you need more fuel, but fuel adds weight, which requires even more fuel to lift that weight off the ground. This loop of diminishing returns is the Tsiolkovsky rocket equation. Because the weight of the fuel is fixed, the only way to beat the math is to throw that fuel out of the engine at a higher velocity. Since engineers cannot change the physics of the equation, they spend their lives inventing different cheat codes, propulsion systems designed to throw mass faster than ever before. The oldest and most rigid solution is the solid rocket, a technology born from early military weaponry, like the Congreve rockets of the 19th century. These engines function by pre-mixing fuel and oxidizer into a stable, rubbery, solid block. It is a simple, potent chemical battery that requires no moving parts or complex machinery. Once the block is ignited, it burns rapidly, creating high-pressure gas that is squeezed through a nozzle to reach supersonic exhaust speeds. However, this design is essentially a controlled bomb. Once the fuse is lit, a solid rocket cannot be throttled down or shut off. It burns until the propellant is gone, regardless of what happens to the mission. Solid rockets provide the raw, immediate thrust needed to fight gravity during liftoff, but they lack the flexibility required for the complex maneuvers of deep space. For precision, Robert Goddard pioneered liquid propellants. By keeping the fuel and oxidizers separated as cryogenic liquids, engineers gained a way to control the fire. This requires incredible mechanical complexity. Powerful turbopumps must force the separate liquids into a combustion chamber at thousands of pounds of pressure. The resulting explosion is funneled through a bell-shaped nozzle, which converts heat and pressure into the downward kinetic energy that propels the rocket. While this adds thousands of potential failure points, it allows pilots to throttle the engine, shut it down, and even restart it mid-flight. This level of control makes it possible to land a fragile spacecraft on the moon or perform precise orbital adjustments millions of miles from Earth. Liquid engines trade away mechanical simplicity for the absolute control required to navigate the solar system. Once a spacecraft escapes the heavy pull of Earth's gravity, massive chemical explosions are no longer the most efficient way to move. For simple orientation, a cold gas thruster can nudge a ship by simply spraying a puff of pressurized nitrogen, much like the air escaping a balloon. For long-distance travel, we use the ion thruster, which represents the current peak of propulsion efficiency. These systems use electricity to zap xenon gas, stripping away electrons to create ions that are fired backward at extreme velocities. Although an ion engine provides only a tiny physical push, it can fire continuously for years. This sustained efficiency is the only way to bridge the vast distances between planets. For most of the 20th century, the rocket equation forced us to discard our most advanced hardware in the ocean after every flight. The Saturn V shown here was a masterpiece of engineering that was largely destroyed just to reach the moon. Modern engineering has finally begun to outsmart the cost of the equation. By landing and reusing the primary boosters, we can launch more frequently without rebuilding the entire system from scratch. But solving the propulsion math only gets us to the starting line. This infographic illustrates a different kind of trap, the biological limits of the human body. As we use our engines to travel further from Earth, our crews face sustained exposure to space radiation and the bone-thinning effects of altered gravity. Reaching Mars requires more than just high exhaust velocity. It requires engineering solutions for isolation, distance, and hostile environments. These biological hazards are the next great walls we must break through. Every rocket launch is a demonstration of human ingenuity successfully executing a heist against the absolute laws of physics.